In this video, I'm going to be going through some properties of power series, and these properties are going to be useful in order to derive formulas for new power series out of formulas for old ones, which is one of the main things we're going to be doing with power series. Now, I'll say that this video relies very, very heavily on two previous videos, and in fact, almost everything that I'm going to be saying is just mashing together results from these two videos. So in the most recent video, we saw that power series often converge uniformly. In a few videos ago, we talked about what happens when series of functions converge uniformly, and in particular, we checked that things like the uniform limit of continuous things are continuous, and similarly, you can take term-wise derivatives and integrals. Okay, so I'm going to be using those properties very, very heavily, and so if you don't remember what those are, I suggest doing a quick review before watching the rest of this video. All right, let's see what the main results are. Throughout the whole video, I'm going to let f of x be equal to the sum k equals 0 to infinity of akx minus c to the k. So this is some power series, and I assume that this convergence happens on this interval from c minus r to c plus r, where r is the radius of convergence of this power series. Okay, so I'm just setting the same notation that I had in the last video. Here's the first theorem. F is continuous on any closed interval from a to b, which is contained within this open interval on which the power series is guaranteed to converge. Okay. What's the proof? Well, it's really just pushing together two results that we had before. We know that akx minus c to the k is continuous for all k, right? It's a polynomial. And we also know that these partial sums associated with the power series converge uniformly to f on ab. Now, that's not obvious, but that was something we saw last video. Whenever we have a sequence of continuous functions that converge uniformly, we know by corollary 8.15 from the lecture notes that in fact f, the limit itself, f, is also continuous on the same interval. Okay, so as I said, very short argument, but mostly it's short because we're pushing together a bunch of very powerful results that we've seen over the last few videos. The next theorem is, in the same situation, the integral from c to x of f of s ds is equal to the sum from k equals 0 to infinity of ak over k plus 1 times x minus c to the k plus 1. In other words, we get a formula for the integral of a function in terms of the power series of the original function. Now, I'll highlight something that is often easy to miss. One part of this theorem is saying that actually this integral does exist, which is otherwise, I think, not 100% obvious. So how do we prove something like this? Well, the proof is going to be fairly similar to the last theorem. I'm going to assume for now that x is strictly bigger than c. The proof is sort of exactly the same for x strictly less than c. By exactly the same argument that we just did, we can see that these partial sums of the power series converge uniformly to the function itself over this compact interval from c to x. And thus, by theorem 8.17, which we saw a few videos ago when talking about uniform convergence of series, the integral from c to x of fs of ds is equal to the sum from k equals 0 to infinity of the integral of the power series terms. That is, we can switch the order of the integral and the sum when looking at a power series. And now, of course, we can integrate this. That's just equal to the sum from k equals 0 to infinity of ak over k plus 1 times x minus c to the k plus 1. Okay, so again, a short argument, really taking advantage of the same two facts, that we have uniform convergence and that we have an integration formula whenever we have uniform convergence of series of functions. Okay. The next argument is going to be probably unsurprising if you've seen the video about convergence of series of functions recently. We have the following: under the same conditions, the derivative f of x is equal to the sum k equals 1 to infinity of k times ak, x minus c to the k minus 1, again for x in the same interval. And again, a key part of this theorem is that actually the derivative exists, which is otherwise, again, not entirely obvious. How do we prove something like this? Well, we recall from way back close to the beginning of the course that n to the 1 over n converges to 1. And so in particular, if I look at the radius of convergence of this power series here, we can see that it's equal to the lim sup of k times ak to the 1 over k. And this k term to the 1 over k, that just converges to 1 by this factor we're calling here. So in fact, this lim sup is equal to this lim sup, that is 1 over the radius of convergence of the original power series. So putting that together, what have we shown here? We've shown that the radius of convergence of this power series is actually equal to the radius of convergence of the original power series. That's important because it lets us invoke theorem 9.9, sorry, not because it lets us invoke theorem 9.9. It's important in about a second. No, it lets us invoke theorem 9.9, which tells us that this sum here converges uniformly on the same interval from A to B, which is sitting inside of its radius of convergence region. Okay. Now we're going to apply corollary 8.22. We've checked all of the conditions of that corollary, and that corollary lets us interchange the derivative and the summation formula for a power series, and so we find that the derivative of x is equal to the sum of the derivatives of the terms of its power series, which is exactly the formula that we wanted to get back at the beginning. All right. So those are sort of the most important theorems about power series. They tell us that we can do sort of the obvious things, interchanging derivatives and integrals, and they also tell us that we get a continuous function. There's one last nice thing to know about power series, which is that actually it's not too hard to figure out what the formula is for the coefficients of the power series. We have the following theorem. As long as the radius convergence r is strictly greater than 0, then the coefficients of the power series for f are exactly the kth derivative of f, evaluated at c, divided by k factorial. How do you prove something like this? Well, when k is equal to 0, this is clear. Otherwise, we can repeatedly differentiate the formula for the power series, taking advantage of this theorem for the derivatives that we just proved. And if we do that, what do we get? We get that the kth derivative of x has the following power series: sum n equals k to infinity of n factorial over n minus k factorial, an times x minus c to the n minus k. Okay. Now, I'm not exactly deriving that formula. It's certainly something that you can check for yourself, for example, using an inductive argument, but I'm not going to sort of do the line by line right now. All right. Once we have that formula, we can just evaluate this formula on both sides at x is equal to c. And on the left-hand side, we get the kth derivative of f at 0. And on the right-hand side, all of the terms are 0 except for the term when n is equal to k. And on that term, we end up with n factorial over n minus k factorial times an times 0 to the n minus k, which is indeed just k factorial ak. And if you look at these two parts of the equation, we can see that rearranging, we get exactly what we wanted. Ak is equal to fk of c over k factorial. I realize as I'm writing this that, of course, I made a typo right here. This should be fk of c, as I say up here. All right, so that's sort of a nice thing. We have a formula for the power series, at least when the power series makes sense. And as an immediate corollary, we get a sort of uniqueness result for power series. So in particular, we have the following. Let's imagine that f of x is equal to some power series, sum k equals 0 to infinity of akx minus c to the k. And some other function g of x has its own power series over here. And furthermore, f of x is equal to g of x in some little interval. Okay? F of x is equal to g of x for some little interval where the radius of that, where this r, giving you the length of the interval, is strictly greater than 0. When that happens, we actually have that ak is equal to bk for all k. Why is that true? Well, we've just seen a formula saying that ak is equal to the kth derivative of f, bk is equal to the kth derivative of g, and of course we know that derivatives of f are given purely in terms of what happens to f and g on some small interval, and so indeed those derivatives must be equal, which means that these coefficients must be the same. Okay. So that's sort of cute. This is a result that tells us in some sense that power series are unique, right? That is, if you have functions that are the same, right, you end up with the same power series. It's very, very tempting to try to make stronger versions of this theorem. Certainly I've tried to do it myself, but I do have to warn you that most sort of natural attempts to strengthen it, that is, most of the things that sort of come to mind first, actually are false. I'm not going to go into a great deal of detail, but it's really helpful to have at least one example. So I'm going to give a short example without all of the calculations, just to give you some suggestion as to what can go wrong. So here's the example. I define the function f of x to be 0 at x equals 0, and e to the minus 1 over x squared for x not equal to 0. And I just want to point out, okay, certainly we can't use this formula for all x, right? Because when x is equal to 0, e to the minus 1 over x squared doesn't really exist. Having said that, certainly when x is getting very, very close to 0, 1 over x squared is getting very, very large. And so e to the minus 1 over x squared is getting very, very, very small. So indeed, this function really is continuous at 0. So this is sort of the natural thing to define there. And actually, it's not very hard to check that f is in fact differentiable at 0. And you can compute the derivative f prime of 0, according to this formula, in fact, is equal to 0. So that's something that you can do sort of by staring at the formula. I'm not going to try to compute higher powers of the derivatives of f right now, because the algebra gets a little bit messy. But in fact, it's true that all derivatives of f are in fact equal to 0. All right, so that was a little bit of messy calculation, or sort of lack of calculation. What's the meaning of that? Well, let's imagine that f had a power series, f of x is equal to sum k of akx to the k. Well, we've just seen that all of these derivatives are equal to 0. And we also have a formula that whenever you have a power series, the coefficients are equal to the derivatives divided by some appropriate number. And so because of those two things, if f was really equal to its power series on some interval, then in fact all of those coefficients would be 0, and so f would be 0. Now f isn't 0, and that tells us that in fact f doesn't have a power series. All right, so there's something that's sort of interesting going on there. There are these funny pathological examples which don't really have power series in the way that we would hope functions would have, and so there's some limitations to using this technology. Now, we're not going to get any further about this in this course. I mostly just wanted to warn you that this sort of thing can happen, and you shouldn't just assume that power series always exist and equal their associated functions. If you're interested in more about this, Math 3121 is going to go into many, many more details. Okay, thanks.